Okay, check. Good. All right, so let's go through our fundamental forces. Give me one with a raised hand. What do we got? Sir? Gravitation. Oops. Hold on, we'll come to there. Gravitation. Sir? Electromagnetism. Cool. What else? Strong. And the weak. Okay. With this, there are force carrier molecules, right? Or force carrier particles, not molecules, particles. What is the force carrier for a gravitron? Or gravitation? So, good, thank you, well done. A graviton. How about electromagnetism? Photon. Okay. How about for the strong force? Gluon. And for the weak force? Cool. Okay, these are the pieces, particle-wise, that are carrying these forces, right? And again, the best analogy I've seen of this is thinking of somebody playing catch, right? If I'm going to put a force onto Ryan, right, and I'm going to play catch with, when I throw that ball, and again, imagine it's a very solid, heavy ball, not just a little tiny softball or a baseball, it puts a force onto him when he catches it, right? That's the thought behind these force carrier molecules. In order for there to be an interaction, you have to have this particle that is doing the carrying of this force. Now, what do they do? Again, we're talking briefly here. With a raised hand, gravitation. What does it do? Like, what's its point? Or how does it work? You with me? So you're thinking about how these pieces actually work. Now we're not doing simple memorization. Yes, sir? Excellent. So you give me some pieces about how it works. That it's about mass, right? That gravity is directly proportional to mass, right? As well as distance, right? And that's even a squared relationship, right? The closer you get, you're not just, so if I have the distance, I'm not just doubling the amount of force, I'm actually quadrupling it, right? It's a squared relationship. So obviously the closer you are, the faster, the more powerful gravity is, okay? And it's actually that warping of space-time, right? Like a bowling ball on a trampoline, right? Or I think Hank used the fruits on a mattress, right? They were pulling down and making that indentation. Okay, how about electromagnetism? Talk me through the thoughts there. Okay, so that's kind of the combination of the two of them together, yeah, that you can use electricity. But what is electricity? Movement of electrons, right? So this movement of electrons actually will set up a magnetic field if you, again, design it in the right way to allow this to happen. Okay. What else about the electromagnetism force? You were going to say something else, or did I already jump into it? So there's these two different pieces, electrostatic force and magnetism. Though we have discovered that, hey, these are actually the same things doing the work, right? We divided them into two pieces in the videos, but they are the same force. Mr. Maxwell, and I talked a bit about him before, that he was the guy who combined these two with a series of 6 equations that said, hey, no, this is all talking about the same stuff here. We cool? Big thing with electromagnetism is you have poles, right? A positive and a negative pole. Every magnet, no matter how small you keep cutting it up, it still has a positive and a negative pole to it. That's what it means to be a magnet. Okay, how about the strong force? What's going on there? I heard some thoughts. Yes?
Holds the quarks and the hadrons.
Okay, so it's holding the pieces of the protons and neutrons together, right? So that's certainly one piece, actually just like gluing the pieces together. But what else? The neutron.
Yeah, the neutron.
Okay. You're close, yeah.
And then like it converts into like a positive or like an up. It was something like
Yeah, I think you're thinking of the weak force, where we've got the switching that's going on. I got you there. But there is something about the actual nucleus. Sure. We have the color pieces there, absolutely. That's talking about the different quarks that are present. But so not only are we holding the individual particles together, but what else are we gluing together? What else is in the nucleus? What's in the nucleus? Protons and neutrons, right? There's no reason for these guys to stay together, right? There's no electrical charge that's holding them there, right? Protons and electrons, the electromagnetism force is what holds them in place, right? Because one's positive, one's negative. But the strong force is also holding that nucleus together, right? Are you with me? Keeping the neutrons and protons together in one place. Otherwise, they would just, go wherever they wanted to. Okay? This is a G. Sorry. Yep, it's a G. And last but not least, our weak force. How does that work? Or what's going on there? Okay. All right. It does have to do with radiation, right? The release of radioactivity. Okay? And this is what we're talking about, some switching. Do you remember? Protons and neutrons. Okay, but what's what? What's where? Check your notes here. Changing a neutron to a proton, right? Again, through the movement of these different quarks, this changing of the ups and downs, right? By the W boson, coming in and changing it, right? So what does that do? Like, okay, a neutron becomes a proton. Who cares? Changes the element, right? That's what we call radioactive decay. Something that once was this one radioactive something that's not stable, the neutron becomes a proton, and of course the number of protons tells you what it actually is, right? Yes, ma'am. It is. Yeah, it's basically what causes that. Yeah. Are you with me? Good refresher. Good as we move through this guy. It's really not in the textbook, to be honest with you. Yeah, we're just kind of pulling it from other pieces of resources. Yes? Yeah, I just put one link that is the link to all 6 of them. 6? Yeah, all 6 of them. Okay, I want to show you this. And I showed you this at one point last year, but I thought it was really worth sharing you again, because sometimes when we're dealing with this stuff, it's hard to keep straight what it is we're talking about. You know what I mean? Because these are just so small little things, and how does it actually relate to our lives? All right? So this is a website that was created, it started back in 2010, and they've done some adjustments to it. But they're basically showing you how big things are. So they call it the scale of the universe, right? So here's us, right? And we're going approximate 1.7 meters, right? So a little less than 6 feet is what they're going average height, okay? And we're going to go downward. We'll come back and go back upward, but we're going to start downward first. So a meter stick, right? Large beach ball at 1 meter. A small beach ball, half a meter. The largest snowflake, 38 centimeters, 0.38 of a meter. Isn't that amazing? Like, that's a big snowflake, right? There's an inch ruler, right? So 12 inches, about 31 centimeters. So you actually have a snowflake bigger than a foot. Isn't that crazy? It's right here. I guess maybe you can't see. You want to turn the lights off? I just don't want you all to fall asleep. So stay with me. That's why I left the lights on. Okay, so I keep zooming in. We get to an ostrich egg, 15 centimeters. It's huge, right? It's a big snowflake, right? A cup, okay, 12 centimeters. Rubik's Cube, about 5.5, which is about the same size as a chicken egg. It's a decent sized chicken egg. An earthworm, my wife's favorite animal. She hates worms. Hates them. 4 centimeters. Quail egg, 3 centimeters. We keep moving down. There's a square inch. Coffee bean, which is slightly smaller than a hummingbird's egg. Here's the coffee bean, yeah. Hummingbird egg there. We keep going down. A grain of rice. Now we're down to 8 millimeters. Sleet, snow, rain, freezing piece. A microchip, 4 millimeters. An ant's about the same size as a microchip. Isn't that crazy? A sesame seed, it always gets stuck in your teeth. The thickness of human skin at the thickest is 4 millimeters. That's the stuff on the bottom of your feet, on the soles. That's your thick, thick stuff. Some people like scrub that off, make it nice and smooth. Not me. That's you, Tanner, you said? Yeah, I understand. Got to keep it looking nice. A grain of sand way down here at 1 millimeter. So again, this is a thousandth of a meter, right? Keep moving. The thinnest human skin's on your eyelids. I don't know if you knew that. That's your thinnest skin. The largest bacteria is the same size, half of a millimeter. It's big, right? Salt crystal, a computer pixel, 0.3 millimeter. A human egg, like, we have eggs, right? The ladies are releasing these little ovums. Are you comfortable that is as big as a pixel on your screen? 0.25 a millimeter. Like, you could actually see it with your naked eye. This little egg. It's craziness. About the size of a period on a piece of paper. Like in your writing, that's the size of the human egg. Who knew? We keep moving down. The width of a human hair, that's about the smallest thing that we can actually see with our naked eye. Is about that size, that 0.1 of a millimeter. So 10 to the negative 4 meters. Let's keep going down. Thickness of a piece of paper is about that same size. Keep going down. Silt and pollen, white blood cells and red blood cells. We're into what we call micrometers now. And you all remember these, right? Different pieces. A micrometer is a millionth of a meter, right? We keep moving down. There's infrared. Surgical masks will block things up to 1 micrometer, so that's pretty impressive. Here's our red light and violet light. So those are measured in nanometers, remember? 300 versus 700. And that's just the length of that piece. Keep moving down. The largest virus is 500 nanometers. Keep moving down. On a CD, boy, I know that's technology you guys aren't super familiar with, but there are actually little holes, little pits that they burn onto those CDs. That's how it stores memory. And that's about 120 nanometers, the depth of those guys. Keep going down. We're down now at the width of the cell membrane. Each cell has that phospholipid bilayer that holds all the contents in. That's about 10 nanometers. HIV virus, about 90. nanometers. We keep going down. The smallest transistor of a microprocessor of a computer, that one little gate piece is about 2 nanometers. It always amazes me that they can actually make things that small. I mean, these are just so tiny. Thickness of a DNA, that's 3 nanometers. Oh, there's way more. We keep going down. A carbon nanotubule is about 1 nanometers in length. Right? Carbon fiber pieces. That's what they're made out of. The proteins. The looping is, remember, proteins basically are these chains of amino acids that make these three-dimensional structures. You A&P folk know what I'm talking about. Those are, again, about 500 picometers. So we're down below a nanometer. A picometer is a billionth, right? Sorry, nano is a billionth. A pico is a trillionth of a meter. We keep going down. Here's some atoms now. A water molecule is about 280 picometers. And this guy makes me chuckle. I like to think that whenever I drink water, I drink Mickey Mouse heads. Because it is, right? Here's the 2 hydrogens and the 1 oxygen. That is the framework they get into. A cesium, that's the largest. That's about 260 picometers, the same size as a water molecule. But that's just one individual atom. Matt, do you want lunch today? Okay, thanks. We keep zooming in. We're at a sulfur atom. We're at a carbon atom, right? We keep rolling down. A helium atom, 31 picometers. And now we're down to a hydrogen, 25 picometers. That's the smallest single element, is hydrogen. Smallest piece. So again, 10 to the negative 11 meters, right? Very small. We keep rolling down. There's our X-ray wavelength. Our electron wavelength. A gamma ray, remember these I'm sure, down to a picometer, 10 to the negative 12. We keep rolling. An atom's nucleus. Okay, so we're past the actual atom themselves. Now we're diving into the actual pieces of it, right? That's about 10 FM, which is called a femtometer. Again, 10 to the negative 15. So we're into the quadrillions here. Let's go back up here. So average size of a nucleus, about 10 femtometers. And here are things we were just talking about, right? Neutrons and protons. Those are about 1 femtometer in width. And of course, neutrons, remember, 2 downs and 1 ups. And a proton has 2 ups and 1 down. That's what that weak force does, right? Changes one to the other. We keep zooming. We keep zooming. And now we're down to that quark level. Right? So we're down to something called an attometer, A-T-T-O meter. 10 to the negative 18, right? So there's your quarks themselves. The electrons, again, 1 attometer. These are very, very small things, right? We keep zooming. We keep zooming. Here is a preon. I actually honestly didn't even know that this existed. The building block of a quark. I thought quarks were the smallest. Nope. I guess there's this preon thing. We keep going down. A neutrino, a high energy neutrino. About 1 zeptometer. It's where one of the things it can come from, yeah. Where it gives it off. We keep zooming. So again, this was a 10 to the negative 21, right? It keeps going down. So here's our neutrino. Tiny little thing. It's a 1 yoctometer. I didn't make them up. I'm just telling them to you. 10 to the negative 24. Right? Here's all the zeros, right? All of these zeros and a 1 of a meter, right? But there's more. We keep zooming in, and this one we've got a bunch of stuff still. So here's 0.1 yoctometer, 0.01, 0.001, 0.0001, 0.00001, 0.0001, 0.00001. We keep zooming, we keep zooming, we keep zooming, and finally we get down to 0.00001 of a yoctometer. It's 10 to the negative 31. And that's where we get these things called strings. The string theory. Has anybody ever heard of this before? That everything in the world is made up of these little strings. We'll talk more about it. This quantum foam, remember the space-time, right? We talked about gravity warping this, that this is what it's made of, this quantum foam. But do you see how small these things are? 10 to the negative 31, right? Look how far up I have to go before I even get to something that we actually think we know about, right? Neutrinos.
That's just theoretical.
Well, I mean, we have evidences for neutrinos. Yes. But beneath that, this is even further below than we can actually see. Are you with me? Like, we can't actually see these little particles. They're much too small. Mind-blowing, right? All right, I'm going to zip up the other side just so we can, so hold on to your hats here as we zoom quickly up. We get back to the human piece. I just want you to see the other direction. So here's floor to ceiling, right? How big your house is. A little bubble car. I'm not sure what kind of car that would be that looks like that, but. Oh, like a VW Bug, but they just can't say that. I got you. Yeah, there are actually worms that are 7 meters long. Thankfully not around here. That'd be like my wife's worst nightmare. Giant earthworm. Okay, here's a cactus, 20 meters, an oak tree about the same size. A big Boeing 747, 70 meters. Has anybody ever seen the redwood trees out in California? Big, huge, 110 meters. Huge trees. Eiffel Tower, about 320 meters. I don't know where the International Commerce Center is. Anybody know where that is? Sears Tower is in Chicago, 442 meters.
Wait, isn't the International Commerce Center,
Could be. I don't know. Somebody can check it, look it up for me. Half Dome out at Yosemite National Park, 420 meters. Angel Falls down in South America, almost a kilometer, 979 meters. We keep rolling. Mount Everest, 8.5 kilometers almost 9 kilometers tall. But the depth of the Mariana Trench, you know, this is the deepest trench in the ocean, is 11 kilometers, right? So taller than Mount Everest, deep. It's craziness. These are some of the moons that are around Mars. Is that Mars? Yes. Okay, I keep going. We're getting on these. These are planetary-sized pieces. If I click on these, it used to be that they would actually give you a little bit of something about what they were. I don't know them all. There's Pluto, the non-planet. Okay, again, about 2,300 kilometers. There's the moon, 3,500 kilometers. Here's the U.S., 4,200 kilometers. So the U.S. is actually bigger than the moon. Isn't that? I mean, obviously it's not circular like the moon is, but spread out. Mercury is only just a bit larger than the U.S., 4,900 kilometers.
Is the U.S. including Alaska?
Probably, because Alaska is a huge area. No, I would assume that they included that, yes. Otherwise, it would be less. There's Mars, just a little bit bigger than Mercury. And there's Earth. Again, almost 13,000 kilometers. Venus, just a bit smaller than us. Again, Ganymede, I can never pronounce that right. That's the largest moon in the solar system. Where is that?
It's under Jupiter.
I think it's in Jupiter, but I'm not positive. There's too many moons. It's been too long since I looked at them. There's Neptune. There's Uranus, not Uranus. Uranus. There's Saturn, Jupiter. And now we're into the smallest star. So you see this? 20,000 kilometers is the smallest star. And are you comfortable that Jupiter's way bigger than that? Like, in all honesty, Jupiter is a failed star. Like, it could have been a star. Saturn, too. Not much. I mean, this is bigger than that, right? 120,000. And if it wasn't for the fact that we had these two planets, because they catch an awful lot of debris. You know, there's like that ring of meteors, or not meteors, what's the word I want? Asteroids, thank you. Between us, between Mars and Jupiter. It's basically held there because of Jupiter's gravity. So it's protecting us.
How long does it take to orbit?
A long time. Yeah, they're big. They're big. It all depends on how fast you're going, where your orbit is. But yeah, they are big, way bigger than that. Because here's us, right?
Would it take years?
It could, yeah, depending on how far up you are. Yeah, how fast you're moving. Okay, here's our sun, which I'm sure you knew this has a name, Sol. Like that actually is its real name. The sun is what we call it. Alpha Centauri, this is the closest star to us. Not how far away it is, but it is about 1 million kilometers. They call that a gigameter. And you know these, right? You remember these prefixes. Alpha Centauri A and Alpha, there's two stars together in the Alpha Centauri system. Both decent sized. Yep, Sirius A as the brightest in the sky. We keep moving out. Pollux, Vega, Aldebaran, Regal. Just so you can see the distance from Mercury to the Sun, right? So here's the Sun, here's Mercury. That is 60 gigameters. So 60 million kilometers, right? And these guys are bigger than that. Like this is that size. Cool? Keep rolling. Denebe la Superba. That's a fun name. The Pistol Star. Here is a little star here that they just is basically one they just grabbed. W. What is that? VV. VV Cephei B is 20 million kilometers, right? And over 1 billion Earths can fit inside that dot. Like that's how, to get back way down to the Earth, I got to go way back down here, right? And again, that's how far I'm zooming out. That you need over 1 billion of those guys to fit in that little dot. We keep going out, zooming out, zooming out. Canis Major, perhaps you've heard of that one. It's the largest star that we know of. Don't worry, they're coming. By the way, here's the distance from the Sun to Pluto. Right? 5.9 million. Sorry, 5.9 billion. We keep going up. So this is a nebula. Basically, the nebula, it looks like two things that are being torn apart. That's what it looks like. The solar system's Kuiper belt, this is basically the outer regions of our solar system. How big is that? 15 TM. TM is this terameter. We're at 10 to the 12 now, right? So millions, billions, trillions. Keep zooming. Keep zooming. The Stingray Nebula. The solar system's Oort cloud. So this is, again, this other cloud of mass matter. That is 1.5 petameters. A peta is a 10 to the 15. So again, millions, billions, trillions, quadrillions. So 1.5 quadrillion kilometers across. And by the way, they're giving you light years now. That's about 0.15 of a light year. So you come to a light year is a very long thing. Keep going.
How long is that in our time?
A light year is the amount of time it takes for light to travel in 1 year. So you're saying in actual years, how much is that? Because it's not time, it's distance. a light year is not a measure of time. It's a measure of distance.
So
They
how
just
long
measure
would
it
it take for us to get
speed of light.
Right, if you could move that fast. We can't even come close to that. Yeah, the fastest something that we've gotten is a satellite that's been accelerating for 40-some years, and that's still only about a third or 40% the speed of light. So no, yeah, we can't come close to it. We keep going out. Here's your actual light year, how much it is. 10 to the 15 kilometers. Again, times 9.5. So it's almost a full. The pillars of creation, how big that thing is. Again, 10 light years across. Here's the distance from the Earth, from our sun to the nearest star. Again, it's 4.3 light years. Millions, billions, trillions, 400 trillion kilometers. Not too far. Just go out for a drive, yeah. You'll be there shortly. The Orion Nebula, again, it is 21 light years across. This is size. We're not talking about distance away. We're talking about how big it is. Right? Now you've got these globular clusters. They keep getting bigger. Galaxies now we're talking about. The Triangulum Galaxy, the Sombrero Galaxy, because it kind of looks like a hat. Our Milky Way Galaxy, how big is that? Oh, sorry, I keep trying to do it with my mouse. 1.2 zettameters. Again, that's a 10 to the 21 meters. All right. Or 120,000 light years across. We keep going out. These are our groups, our galactic groups. Hang on one second. We keep going out. We keep going out. The observable universe. Just how big we possibly can be. How far we can see. All right? Humongous. Tiny, 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 and humongous. Just kind of an interesting piece. Where I want you to start thinking, and again, I apologize for keeping you 30 seconds here. I want to think about what we can do with this information. I have a whole list of product type pieces I was going to put up, but we'll talk about this tomorrow. Because I want us to I don't want to just test you over this material as far as the forces that we've learned about. What can we do with it? Can we make something? So get that kind of percolating in your mind between now and when I see you next time. Thanks for the extra minute. Adios.